In topic 4, we have to multiply probabilities together. There is a formula that says if you have the combination of two probabilities, you want A to happen and you want B to happen, asking for both to happen, we are going to be using individual probabilities, but multiplying them together. Very, very effective strategy because we won't really be drawing a lot of sample spaces, as multiplying does create a substantial amount of outcomes, especially when we say use a deck of cards. Now, because we can now leave sample spaces out of it, we could answer certain questions. Let's say I have two 6-sided die. I could pretty quickly ask, what is the probability of on one die rolling a 2, and then on the other die rolling a 4. And I could really just break this down, and the and does kind of give it away, where I can now break it into say, well, all I have to know is what's the probability of rolling a 2. All I have to know is what's the probability of rolling a 4, and I can multiply them. I don't really have to draw out all 36 outcomes. It will naturally take care of itself. There is a 1 out of 6 chance, and then a 1 out of 6 chance, and then together that's a 1 out of 36 chance of rolling something very, very specific, which would have been identical had we actually gone through, the laborious process of showing 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then locating that very, very specific outcome, the outcome where you roll the 2 on one die and then a 4 on the die. That's the outcome that I calculated, but it was out of a total of 36 total outcomes here. 6 by 6 would have been 36 total. And so this multiplication trick really does come handy when we start asking for some bigger kind of questions. But there are two scenarios that kind of show up in two very, very big vocabulary words. Let's talk about, a nice situation and a very common situation where we say, have a deck of 52 cards. And if you're not super familiar with a deck of cards, maybe, find a picture or kind of follow along here. I'll help you out. There are 4 aces in a deck of cards. And I could ask, what is the probability of getting 3 aces in a row? Now, there's a chain of events happening here. What happens when you get the first ace? Now, and we have to be really, really specific on how this chain of events is happening. When the first card is drawn, we can put the card back. It can just become part of the deck again. They could reshuffle, whatever they need to do. They can put the card back. Now, in this case, you'll notice that the probabilities really aren't changing at the moment. During the first ace that they're trying to get, we'd have to say there's a 4 out of 52 chance. There's only 4 aces. There's a total of 52 cards. And then, we want another ace. But if we put the card back, the deck is still brand new. There's still 52 in total. And there's still 4 aces left. Put the card back again. Now, and then we still want to get that third ace. And again, the deck is fresh. The cards are all back in. We have 4 out of 52. And nothing really kind of affected each fraction. It was a brand new situation in theory, almost every time we were pulling this card. Now, this is what we would call independent. Each fraction didn't rely on the other. The chances never changed over time. Every event was kind of its own completely separate probability. The past didn't influence the future. The future didn't influence the past, if you think about that, but everything was totally independent. And the giveaway for that usually is that the universe stayed consistent throughout this whole process of trying to get 3 aces in a row. Now, these numbers get really big, really fast, and let's see if my calculator can even handle these huge fractions without kind of getting a little bit upset. Now, yeah, the first thing I see when I multiply this out on even a graphing calculator is that it's telling me 4.55 e to the negative 4. Now that's not a nice number. So I'm going to try and convert. Oh, my calculator for it does this. Not all of them will. If I convert this into a fraction by pushing math, enter, enter, it is nice enough to do this and tell me that it is 1 out of 2,197. And that is the reduced probability. Now, if we didn't really have a fancy calculator and we didn't really have the ability to convert into a fraction, especially once these fractions get quite large, we kind of maybe have to know how fractions work a little bit, where it's the top times the top times the top to get 64, and it's the bottom times the bottom times the bottom, which is 140,608. And that is the true probability. Now it reduces, 64 divided by this number is, again, reduced to 1 in 2,197. So extremely unlikely that you would be able to get 3 aces in a row in a deck when these cards are being picked at random. Very, very unlikely. And as we start multiplying probabilities, you'll find that we get these really, really ambitious kind of outcomes. Now, if I set up the exact same thing, that way. However, we don't put the card back. This is usually called without replacement. The story does subtly change. We still need to pull out that first ace, and then we still need to pull out another ace, and then we still need to pull out that third ace, but we're still going to be multiplying. When we're starting, there's 4 out of 52. Now, this is just still the first card. It's still the first ace. But now, as I go to the next event, there's now 1 less card. Because we're pulling it out. Because we're not putting that card in. We're not taking out all 4 of them. There's just 4 options. There's still 4 in the sample space currently. But we're only picking out 1 card in the first stage of this question. So now there's only 3 aces and there's still only 51 cards in the deck because we only pulled out 1 card, but there'd still be 3 aces, but only 51 cards left. Now we're 2 cards in. That second card came out. Now we have even 1 less card. And these are our countdowns, our probability countdowns, where now there's only 2 aces and there's only 50 cards in total. And there's where we get to multiply these three fractions together. And we can break these outcomes totally into individual basic probabilities, but the multiplication of these is going to help us out. And there is no way I'm going to draw this out as a tree diagram or some sort of probability chart. No way. Drop it. So as I type this in, 4 divided by 52 times 3 divided by 51 times 2 divided by 50. Again, my calculator is being kind of silly. It's telling me it's 1.8 times 10 to the negative 4. That's not really a nice way to write this number. But as a fraction, it is going to give me 1 in 5,525. So in a more realistic scenario, like say playing a game of poker, where cards are being dealt out and people are keeping the card and the deck is getting smaller, it is incredibly hard to get 3 aces in a row compared to if those aces kept going back in. And this is usually called with replacement. Now notice that universe was changing. Getting this first ace changed the probability. It changed the universe. If we got the ace, there's 3 out of 51. If we didn't get that ace, there would be 4 out of 51. And it depends what happened before. Now, we always assume you're successful. If we're going for aces, we always assume you get the ace, so the countdown occurs. We're trying to find the chance of being successful. But there was a modification in the universe. Each event depended on what happened before. And this style of multiplication we call dependent. The whole chain of events was dependent on the outcome before. As in the countdown, taking out that card changed everything. And we multiply these probabilities together to create new combined total probabilities in a multiplication scenario.